Hello, and welcome to this presentation on gas chromatography. My name is Jamie, and I'm going to walk you, the viewer, through identifying the parts of a gas chromatography instrument. We'll be using the GC in the laboratory to identify the presence of methanol, ethanol, isopropanol, acetone, and ethylene glycol in various patient samples. Before we begin, I want you to think about the following two questions. What is the physical state of our sample? And how does that physical state of our sample relate to our method of detection? When performing chromatography, the sample needs to be in the same physical state as that of the mobile phase before being applied to the column. In the case of gas chromatography, we're using a gas mobile phase, so we would want the sample to be a gas as well. For liquid chromatography, the sample and the mobile phase should both be liquid. In this lesson, we're going to learn about the components of the GC instrument, and we'll learn about the sample interactions that occur with each component. Here in the lab, we're currently using two different types of GC setups. Here we have the Shimatsu Headspace plus its 2010 GC. This is the instrument that we're currently using to detect methanol, ethanol, isopropanol, and acetone within our alcohol scan test. We covered the mechanics of headspace sampling in the previous presentation. In this presentation, we're going to focus on the 2010 GC portion. And here is the Shimatsu 2010 GC that we're using for ethylene glycols. As you can see in this picture, the autosampler and injector are significantly different than that of the Headspace autosampler. However, the GC portions for both instruments are the same. Now let's identify the different parts of the GC instrument. As we look at each component, we're going to review how our sample is behaving. It's important to understand how the sample interacts with each component because these interactions are what are going to produce our resulting chromatography. Here's a diagram of the whole GC instrument. We're going to keep referring back to this diagram as we look at the individual components. The path of the sample consists of the following actions. The syringe pierces the rubber septum of the injection port, and the sample is injected into the glass liner. That glass liner is inside of the injection port, and inside the injection port, we're going to heat the temperature very high in order to vaporize our sample. At this point, the gaseous sample is going to mix with the gaseous mobile phase inside this port before making its way onto the column. Once on the column, the sample molecules are going to bind to and elute from the binding sites contained in the column packing. As the sample elutes off the column, it travels to the flame ionization detector, or FID. The FID detects carbon ions that are produced as the sample molecules eluting off the column burn up in a flame. The concentration of the carbon ions is directly proportional to the signal detected by the FID. Finally, the computer is going to graph this response and integrate the signal, turning our result from the chromatogram into something that we can read. The first component, which was not shown on our previous diagram but is seen here, is our autosampler. Most instruments have some form of autosampler. This is the portion of the instrument where we're going to load our sample vials. In the lab, we have two different types of autosamplers. The autosampler here is for the GC that we're using for ethylene glycol detection. Ethylene glycol detection uses direct sampling. That is, the sample is injected directly into the injection port. Here we can see the autosampler tray mounted on top of the instrument. The autosampler and injection module for this setup are two different modules. If you remember from the previous video, the Headspace autosampler includes the heater, mixer, syringe, and injection port all in one complete module. The autosampler delivers the sample vial to the injection port where the sample syringe aspirates our sample. Then the sample syringe pierces the rubber septum of the injection port and injects the sample. There is a glass liner on the inside of this module, as we can see here, where the sample is collected, heated, and mixed with the carrier gases. Here's a picture of the auto-injector module on the ethylene glycol instrument. And this is a closer look at that module with the door open. We can see the syringe here, which is usually programmed to aspirate a small amount of sample, about a microliter, and it will inject the sample onto the column. The syringe pierces the rubber septum inside of the inlet of the injection port and injects the sample. If we remove the auto-injector, we can see the top portion of the injection module. This portion contains the injection port, where the sample will be injected. The injection port is sealed using a rubber septum to ensure that no gas escapes. This rubber septum does wear out over time and will require replacement to ensure optimal chromatography. The remainder of the injection module can be seen inside the oven. Prior to sample injection, the module is heated to the appropriate temperature required for sample vaporization. Inside the module, the carrier gas is mixed with the vaporized sample before the whole mixture moves onto the column. You can see the connection to the column here. Inside of the module is where the glass liner sits. There are different types of glass liners that can be used depending upon your needs. In general, they help with activating samples and catching the buildup of harmful residues produced during vaporization. Like the rubber septum, the glass liner needs to be replaced periodically to ensure good chromatography. Here is a picture of the column on the inside of the oven. The sample enters the column at the base of the injection module and moves through the column and then exits the column at the connection for the FID. The oven keeps the column at the correct temperature, or temperatures if we're using a gradient, which are all method dependent. Once the sample mobile phase gas mixture enters the column, the sample molecules bind to and elute from the binding sites within the column packing. Gas chromatography requires columns with a large amount of surface area to allow binding to occur. Most columns are 15 or 30 meters long and 1 to 5 microns in diameter. The column pictured here is a silica glass column, and it contains a coating of stationary phase on the inside. Here we're using a column with a polar stationary phase to detect ethylene glycol, which is a polar compound. If we were looking for a nonpolar analyte, we would use a nonpolar compound. The binding that occurs inside of the column is referred to as reversible binding. This is necessary because we want the analyte to bind to the column temporarily as a means of separating or extracting it from the sample mixture. Once we have provided enough time, the binding will reverse and the analyte will elute off the column. The process of binding, elution, detection is what produces peaks on the chromatogram. Column health is important for good chromatography. Binding sites wear out over time due to routine use and buildup of residues in the system. Routine maintenance can extend the life of the column, however, it will too need to be eventually replaced. Here is a cross-section picture showing the inside of the FID. The nozzle sits at the end of the column and produces the flame while the collector detects electrons produced as molecules burn. This diagram shows the process a bit more clearly. Here we can see the path of the sample as it travels through the column, into the flame, and through the detector. This diagram is also nice because it shows the input for the makeup gas used to power the flame itself. In our ethylene glycol method, our carrier gas, or mobile phase, that's flowing through the column is helium, while our makeup gas is a mixture of hydrogen and air. The types of gases, their mixtures, and their uses are all method dependent. The FID is used to detect carbon-hydrogen bonds. As the molecules of analytes burn, these bonds will break and produce carbon ions. The collector detects these carbon ions and translates the signal into the peaks that we see on our chromatogram. The concentration of carbon ions produced by the analyte present in our sample is directly proportional to the signal detected by the FID. Let's relate this back to our ethylene glycol testing. Ethylene glycol has a chemical formula of C2H6O2. That means there are a total of 4 single carbon-hydrogen bonds per molecule that could potentially be detected by the FID as our sample burns. Keep in mind that only one molecule in 10,000 will release an electron to be captured by the detector. The final component of any chromatography system is the computer and its integration software. The computer is responsible for maintaining communication between each part of the instrument. For each analytical method, there is a subprogram that controls the autosampler and injector, the flow and mixture of gases, the column and oven, and the detector. The integration software is responsible for performing the complex calculations that produce our testing results. In this picture, we can see the real-time run screen for the Shimatsu. The top yellow portion is where you can view peaks as they're coming off the column in real time. The bottom portion of the screen, there are a series of tabs for each subprogram. Each of these tabs contains the operating parameters for each of the subprograms. This brings us to the end of our video. The basic instrumentation presented here can be applied to most brands and types of GC systems. In future videos, we will take a closer look at the chromatographic data and how variation in the system can produce different types of peaks. Thank you for watching.